Morning.
Large. So they could be order a few tens of meters per day up to sometimes 100, a couple hundred meters per day. And an open question is to what extent are those vertical velocities important for generating tracer fluxes, or in some cases, particulate POC fluxes, particulate matter, from the ocean surface into the interior. So what I've got my title here, what we talk about when we talk about submesoscales, the things that people really think about and care about are these properties, right? So the intensity of the submesoscales depends a lot on how strong are those fronts, right? So you establish a horizontal density or a buoyancy gradient, so dB dx here, that's very sensitive to the strength of that mesoscale strain. And then the other thing that's really important is the stratification in the upper ocean. And that can be both how deep are the mixed layers, and you can think of that as a control on how much potential energy might be stored in these horizontal density gradients. And then a second property that's received less attention, but I think is really important, is how strong is that stratification right at the base of the mixed layer, which governs the efficiency of those submesoscale motions in the mixed layer and actually enabling exchange from the surface layer into the interior. So these are the different properties we're going to think about and how they vary from place to place in the Southern Ocean.
Andy, this is Randy. Could I ask you to clarify? So I'm puzzled on the comment about the mixed layer depth relationship to potential energy stored, which I tend to think of as the associated with a deeper sloping thermocline or pycnocline and all the potential energy associated with that. So how does that? Yeah, it's just yeah.
I'm not going to go into a lot of detail about this idea of, well, I'm not going to go into technical detail of how one sort of arrives at the strength of the stream function in the upper ocean, but suffice it to say that the sort of classic picture of baroclinic instability that you have in the interior, that when you have this sort of broad, sort of very large scale tilting isopycnals, they can be relaxed via a baroclinic instability and generation of mesoscale eddies. The same thing happens in the mixed layer, and in fact is typically called mixed layer baroclinic instability.
Oh, okay.
So when you have this frontogenesis, you have the same sort of picture happening, that there's potential energy stored with those tilting isopycnals. And if that happens over a relatively small fraction of the surface ocean, then there's just less potential energy there to extract. And if the mixed layers are deep, you have more potential energy. I'll show that a little bit in a minute.
Thanks.
Yep, sure. As I mentioned, I'm going to mostly talk about observations today, but I would be remiss if I didn't show this beautiful movie. What you're looking at here is a global ocean simulation that was run by some of my colleagues up at JPL, most importantly, Dimitris Menamenlis. At the time, this simulation is now at least 5-6 years old. It was the highest resolution simulation that had been run globally. And what you're looking at is the surface vertical vorticity. And of course, the reason why we're showing vorticity here is what I said before, that we know the submesoscales are very strongly impacted by mesoscale structures that are sort of a signature in the vorticity and also in the strain.
Andy, what's the color scale on this picture?
Yeah, so I don't have a color bar. I'll have one in a subsequent slide. When you start seeing these darker colors, you're seeing the relative vorticity sort of approach the Coriolis frequency. So dark colors here is about half Rossby number. So the ratio of the vorticity to Coriolis frequency is about a half. And the only thing to kind of point out here is that even at what you're really seeing is the mesoscale, right? And then we're going to talk a little bit about how that impacts the submesoscale. But you can see that it really varies throughout the ocean. So an obvious place where it varies is the western boundary currents. I'm going to talk a lot about the Southern Ocean. You can see that the Southern Ocean is very patchy. I'll talk a little bit about why that is. And then as you watch this movie run, we're getting into sort of Northern Hemisphere winter. If you look, especially in the Atlantic on the upper left-hand side here, you can see this region darkening. And so you have this real seasonality, both in the Northern Hemisphere and the Southern Hemisphere. We'll talk about why that is. Now, part of the reason for showing this video as well is I'm really just going to provide one slide of motivation for why submesoscales are important at a global level. And it gets back to this idea that the submesoscales could be very important for tracer fluxes in the surface ocean. And so I'm just choosing one tracer here, and that's the heat flux. And what you're looking at is analysis of the output from that numerical model I just showed you Shansu was a postdoc both at JPL and Caltech, and he did a lot of work looking at this model output and essentially filtering the heat fluxes to look at the contribution from the submesoscales. And so in the upper left, you're looking at the vertical heat flux just at 40 meters depth. So that's important. And you're looking at northern hemisphere winter, and you can see that most of the northern hemisphere lights up, certainly stronger in the western boundary currents, but it's much weaker in the southern hemisphere. And when you move to the northern hemisphere summer, you see the southern hemisphere light up. So there's some real seasonality here again in both hemispheres. The other thing to say is that these values are large. Okay, over most of both hemispheres, the heat flux at 40 meters is on the order of many tens of watts per meter squared. In some places, it's up to 100 watts per meter squared. And it's all more or less single signed. So at 40 meters depth, it is upward. And this is that tendency to take where you have these horizontal density gradients, and you can think about them as horizontal temperature gradients, and a relaxation of that density gradient, bringing warmer water towards the surface and colder water back towards depth. Now, as you go to deeper layers, you'll begin to see that this sort of uniform upward heat flux changes, because that's mostly a surface property. But because this is at 40 meters, it also implies that there's some convergence near the surface. And in fact, when you compare this high resolution model to weaker models, you actually see a warming of the surface. And that's very interesting. Some mesoscales can have this net upward heat flux, but to be a little bit cautious because this is not a coupled model. And I'll maybe get into that a little bit later at the end of the talk. But globally, it's, these terms are as large as other terms in the surface heat budget.
Hey,
so,
Andy,
yep.
Sorry, this is Jamie.
Hey, Jamie.
I'm staring at the winter, the northern hemisphere winter, and where the fluxes are negative. How do you interpret that? Is that, I'm trying to think of what the sign means, kind of physically, what processes, because there's this band of positive, negative kind of alternation.
Yeah, so this is happening up in kind of like south of Greenland.
Yeah, and Tail of the Grand Bank's my favorite.
Right. So the other thing to say in here is that this, I don't immediately have an answer, Jamie, but this includes all processes, at least that this model resolves. So sort of at scales of maybe 5 kilometers, maybe even a little bit coarser than that. And in addition to that relaxation of the front that I talked about, there may be other processes like wind front interactions that are not necessarily going to be single signed, like a mixed layer instability. And so I think over most of the ocean, the fact that this is mostly positive is that is the dominant process, that the submesoscales are trying to relax fronts. But there may be other things happening. And in particular, if you look just south of Greenland, there may even be some convection happening in this model. That could change what this looks like.
Okay, thanks so much.
Sure. Okay, so just for the next couple of minutes, what I want to do is maybe just give a little summary of, I said, some of the key lessons that we've learned from submesoscale dynamics in the mid-latitudes. And, so the first place that people went to look at the importance of submesoscales was in the western boundary currents. So this is a zoomed in snapshot from that same numerical model. On the left here, this is the Kuroshio extension. You can see Japan there on the left. And again, you're still looking at the surface vertical vorticity, and the color bar is down here. So these dark colors are at least like half of the about Rossby number order of half. And as I've already said, that the ocean mesoscale very strongly shapes the submesoscale. So when you go in and actually look at the vertical heat flux, again at 40 meters, so I have got this box here, and then I've zoomed in on it in the upper right, you can see the streamlines, these very coherent mesoscale eddies. And where the submesoscale heat flux lights up is all along the periphery of these eddies. So again, it's in these straining regions that you're seeing this very strong vertical heat flux be generated. And if you take a slice through that section, so along that green dashed line, that's what's shown on the bottom right, again, you can see very clearly that it is in those places where you have strongly tilting isopycnals at the base of the mixed layer, generating these strong heat fluxes at the edge of the eddies. The other thing that I actually just sort of mentioned briefly to Jamie, the other thing that we learned in these regions of strong fronts and strong geostrophic jets is that they can be important wind front interactions. And one important one that I'll talk about a little bit as we go forward is that if you have winds that are aligned in what we call a down front direction, so in this case, you would have strong westerlies coming off of Asia, flowing or blowing to the east, and along the direction of the Kuroshio extension, you can have an Ekman transport that carries, in this case, water from the denser side of that front across the front into the lighter side and enhance, essentially arrive at an unstably stratified configuration and enhance turbulence and enhance mixing. Two other things that we've learned is, and I showed this a little bit in the numerical simulation, is that the intensity of submesoscale motions exhibits a strong seasonal cycle. And kind of the first way that we realized this from observations was actually looking at kinetic energy spectra. So here's a paper that's cited a lot that was led by Joran Kallies when he was a graduate student. You're looking at the power spectra of kinetic energy, taking from ADCP data along the Oleander line, which is in the Western Atlantic. And there are two curves here, one for wintertime at 50 meters depth. So on the x-axis is wave number. And in the lower panel here is summer at 50 meters depth. And if you look in particular at your larger wave numbers or smaller wavelengths, what you see is that during the winter, you have an intensification, you have more energy at the smaller scales. And how this comes out in terms of the spectra, people think about this in terms of the slope, is that there's a shoaling of the slope. So that curve looks more like k to the -2 in winter months, whereas during the summer months, again at 50 meters, the energy drops off more rapidly at the small scales and looks more like you would expect for quasi-geostrophic flow, which has a slope of k to the -3, with a little tail there indicating that internal waves can have an important impact at the small scales on the energy spectra. So that's a very statistical approach, but perhaps a clearer picture if one wants to look at time series. I'm going to show you in a minute a year-long time series that was acquired from a very small region in the northeastern Atlantic. So this was part of the osmosis project that I was involved in. This was a region that was occupied with 9 moorings and 2 gliders for an entire year. And if we think about what gives rise to this seasonality in the submesoscale dynamics, it's largely due to the seasonal cycle of the mixed layer depth. So if you focus just on the top panel, you have depth on the y-axis here, time is on the x-axis. So to orient yourself, 0 here is January 1st. This was fall 2011 to summer 2012. That black curve is the mixed layer that's deepening throughout the winter, can reach depths up to 300, sometimes close to 400 meters throughout the winter, and then shoals. And the color is showing potential vorticity, which for the most part is a pretty good proxy for the stratification. And so you can see there's a strong stratification at the base of the mixed layer in the summer, and that slowly gets eroded with time. And so, part of the change in the intensity of submesoscales is the fact that in winter you have these deeper mixed layers. If you have these fronts, there's more potential energy stored in them. But the other thing that's really, I think, really interesting in this plot is not only is there going to be a seasonality or temporal variation in the intensity of the submesoscales, there's also variations in the ventilation. And the way I want to point this out is if you look deeper in the water column, where you see that darker water, which indicates low potential vorticity and that it's a signature of it coming from the surface, is really not throughout the winter, but it's really in late winter. Right? So even as those mixed layers deepen, you need time to erode the stratification at the base of the mixed layer to efficiently transfer properties from the surface layer into the interior. And so if you're interested in this, Zach Erickson spent some time looking at sort of the importance of that stratification at the base of the mixed layer on tracer transport into the interior. And you really need both deep mixed layers and a weak stratification at the base of the mixed layer. And you can see that a little bit if you look at the apparent oxygen utilization time series. Again, you see that those smaller values, which are a signature of surface water, are more effectively getting into the interior later in the year.
Hey, Andy, can I ask a question?
Yep, sure.
This is Melissa. If those little features in the PV and the oxygen, if it's sort of in a long isopycnal process, are they coming from a place where the mixed layer was actually deeper than what's shown here? Or how do you think those got down?
Yeah, so that's a really good point. I mean, because this region's so small, you're essentially looking at a 1D time series. And so those PV anomalies, low PV anomalies, low AOU anomalies are not necessarily locally generated. I don't think necessarily, though, that those mean that you had a mixed layer that got as deep as 500 meters. I think what happens, so Jorn Kallis, who's a physical oceanographer here at Caltech, has done some work on looking at the vertical structure of these submesoscale overturning circulations. And if the stratification at the base of the mixed layer is weak, then you can get those vertical velocities penetrate to depths deeper than the mixed layer depth itself. Which, okay, for those who are really deep into this, the sort of classic parameterization for those submesoscale velocities comes from some of Bela Fox-Kemper's work about a decade ago. And in that parameterization, he basically assumed that the base of the mixed layer was a solid wall. And in that parameterization, the vertical velocities by definition go to 0 at the base of the mixed layer. And for more realistic stratifications, I think you can get, we're still kind of working on this, that you can get vertical fluxes that penetrate below the base of the mixed layer.
That's great to hear.
Yeah. Yeah, and well, okay, maybe I'll come back to this at the end, but there are other reasons to believe that you can also get strong submesoscale velocities even below the base of the mixed layer, as long as you have regions of strong strain. If you just generate strong submesoscale fronts in the interior, you'll get submesoscale velocities down there too.
Andy, this is Tom.
Uh-huh.
Am I hearing you say that these could be the result of penetrative convection?
No, not necessarily. I think so. Melissa's right that these are still thought of as largely along isopycnal fluxes. Just what you would see if the stratification at the base of the mixed layer is weak is that mixed layer, what you define as the mixed layer is a little bit arbitrary because it's usually some difference criteria. And if there's not a strong sort of change in those isopycnals don't become horizontal at the base of the mixed layer, the vertical velocities will penetrate deeper than what you might just define as the mixed layer. But it's not necessarily convection. There could be convection if you have these wind front interactions that I mentioned previously.
Okay.
I think the differencing, sorry, this is Amit. One last comment, Andy, that was very well explained. It's probably the result of averaging over many submesoscale. What you're thinking of a mixed layer and the stratification of the base of the mixed layer is really an time average quantity over some long enough time scale compared to the submesoscale fluxes. And what Melissa is really describing is sort of the phenomenological description of many of these boluses happening along isopycnal. So I don't think it's either or. I think one is more a time average picture of the process that Melissa was talking about.
Yeah,
there's some work that Sanjeev and I did early on this.
Yeah, thanks, Amit. Okay, so that discussion is really helpful. So if I just sort of summarize some of I'd say the 4 lessons, as many things that we've learned. The mesoscale shapes of submesoscale, wind front interactions can be important. You see a seasonal cycle in the intensity of submesoscales, and the contribution of submesoscale motions to ventilation will vary throughout the year, and it may not only depend on the intensity of submesoscales.
Andy?
Yep.
I hate to interrupt again, but could you go back to that, go back to the previous slide? Those oxygen signals that you see at 400 meters depth, they are an awful lot deeper than your mixed layered, your black line, so to say. So I agree that it's probably not penetrated convection, which is not a very efficient process.
Right.
But we're still talking about a substantial subduction going on here. If you're moving oxygen from 100 meters down to 400 meters, it's these are. I mean, this is almost like you're saying that that density. No, I'm still having a problem.
Tom, is
what's going on there.
I think, as Andy correctly said at the beginning, the mesoscales can act as the chimneys along which these submesoscale processes can interact. So you can have preferential subduction along the mesoscale that can go much deeper than what one would generically think.
That's right. So there's a really, Tom, there's a really nice paper that I was not involved in that was not looking at the glider data from osmosis, but the mooring data. So again, 9 moorings within essentially a 15 kilometer by 15 kilometer box. So you could actually start to really look at the small scales. And it was a paper led by Zhelong Yu last year showing that, again, that there's these very large vertical velocities that happen all the way down to almost down to 1,000 meters. From actually, they diagnosed the vertical velocities from looking at the divergence of the horizontal velocities.
Can I ask that you pass that reference on?
Yes, I will do that. I will do that.
Thank you very much.
So keeping an eye on time here. So those are the lessons from the mid-latitudes. And then if you think about what do we know about the Southern Ocean, region of intense kinetic energy and mesoscale stirring, region of very strong geostrophic fronts and jets, relatively weak vertical stratification compared to the rest of the ocean, which may mean you have deep mixed layers. And you have a band of strong westerly winds, at least over the Antarctic Circumpolar Current, that can give rise to this down front wind configuration. So you would think of the Southern Ocean as being, wow, this is going to be a place where the submesoscales are absolutely going to be important. But there are a few things that you need to keep in mind in which the Southern Ocean is quite different from the mid-latitudes. So the first thing is that the annual cycle of sea ice growth and melt has a very important role in setting surface stratification. So remember to keep in mind that every year, sea ice extent around Antarctica extends to something like 20 million square kilometers, and then it melts, almost all of it melts back every year. So you melt back to about 3 square kilometers. So there's a huge freshwater cycle in the surface ocean. And of course, because there's no continents to the north, that sea ice can expand and mostly melts in around the polar front. There are also, in ways that are slightly different than the mid-latitudes, sustained, strong, along isopycnal tracer gradients due to the fact that a lot of density classes are ventilated at the surface of the Southern Ocean and yet connected to deep water in the Pacific and the Atlantic basins. And then because of the weak stratification, flow topography interactions can be quite important in setting both the structure of the mesoscale and the submesoscale in the Southern Ocean. And so, okay, so what I'm going to talk about for the remainder of the talk, again, is this idea. I'm going to summarize some of the results from a few different studies. Mostly, I'm going to be looking at observations from ocean gliders. As I mentioned before, these platforms have a lot of benefits. You can leave them in the ocean for a long time and start to have a statistical picture of what the surface ocean properties look like. They have some drawbacks. They move through the water fairly slowly at about only 20 kilometers a day. And so one has to be a little bit careful about what one can infer from these types of observations. But over the past 5 years or so, we've been involved in quite a few studies in the Southern Ocean in quite a few different regimes. That's what I'm showing in the bottom there. And I'm kind of going to focus on 3 of these, one in Drake Passage, a Chinstrap program, one south of Africa that was specifically to look at submesoscales in the marginal ice zone, and then a recent study where we deployed some gliders in a large standing meander of the ACC. And so there are some surprises. So the first study I'll show, this is not necessarily going in chronological order, but provide some motivation. In 2016, we had the opportunity to deploy a couple of gliders in Drake Passage. And the initial goal was actually just deploy it in the southern part of Drake Passage along with a surface wave glider. And it was specifically to look at wind front interactions. The wave glider, unfortunately, had some problems with its battery, and so was recovered almost immediately. And we said, let's on the fly sort of figure out something more interesting to do. And we say, wouldn't it be great if we could get across and sample some of the large fronts in Drake Passage? And of course, it was late fall, early winter. There were quite a few storms that went by, and I was extremely excited. This is going to be just going to be crazy submesoscales. There's going to be really strong ventilation into the surface ocean. It's going to be an incredible data set. And as we started going from south to north across the southern part of Drake Passage, this is what the density field looked like. So this depth on the y-axis, distance here goes from south on the left to north on the right. And there was just this really shallow, so maybe 40, 50 meter mixed layer, and just incredibly strong density gradient at the base of the mixed layer. It was just this cap of fresh water right at the surface. And what we think happened was, although there's actually not a lot of sea ice in Drake Passage itself throughout the year, a lot of the sea ice that melts in West Antarctica, so on the western side of the Antarctic Peninsula, gets advected to the east, and there was this advection of fresh water into the southern part of Drake Passage that just ended up with a really shallow mixed layer, very strong stratification at the base of the mixed layer, and just very little variability in the southern part of Drake Passage. And as far as we could tell, there was very little submesoscale activity and little ventilation as well. And so,
do you see any strong salinity gradients on any length scales there in the
shallow? So this slide here is motivation. I mean, let me show you actually. I'll spend a little bit more time on the observations we collected from the marginal ice zone area, and absolutely, it's really, the story there is really kind of interesting. So a couple of years later, we had an opportunity. This is a project that was actually led by Seb Svart, although we participated with some of our Caltech gliders. And the goal was to actually, we weren't doing measurements under ice, so we weren't actually in the marginal ice zone itself. But you can see here on the lower left, there's a time series on the x-axis and latitude on the y-axis that should be labeled. And the color there is sea ice concentration. And so you can see us putting the instruments in there just at the end of December, sort of almost immediately after the ice went away. This picture in B is what that area looked like only a few days, probably maybe almost a week, but just before we put the gliders in. And what we had in the water were two different platforms. So the sea glider that I showed on the previous slide, doing this butterfly pattern or bow tie pattern that you see in the bottom right, and then also a sail buoy. So this is an autonomous vehicle that's a surface platform. And so we had high resolution meteorological data at the surface, along with the sort of in situ measurements from the glider itself. And so I think what it was alluding to is that when, in this region, which is south of the polar front, the density differences obviously can be much more dependent on salinity than temperature. And so you can see this very clearly here. This is a couple months time series of surface salinity and temperature. So time is on the x-axis. The blue here is salinity. The orange is temperature. So you can see as we go from December to the end of February, there's a slow but steady warming of the surface ocean. And yet the density, which is shown in gray, at least its small scale variability, is almost completely dependent on the salinity. And so if you look at those two dashed lines, we zoom in on that region in the lower left there, and you can see, so this is time on the axis. I'm going to show you density gradients in a minute, but you can see this very small scale variability. And so the picture that you have here is when that ice melts out, especially when you're right at the edge of the marginal ice zone. Again, this idea of the mesoscale stirring is very effective at taking that large scale gradient in surface salinity, which gives you a large scale density gradient, stirring it up and generating density gradients at very, very small scales. And that is effectively what you see here. So this is a measure of the intensity of those density gradients on the y-axis. And if you like to think in terms of density gradient, that's kilograms per meter cubed divided by kilometers. Or if you like to think in terms of a buoyancy gradient that I typically think in terms of, these values are pretty strong. So 0.04 is 4 times 10 to the minus 7 inverse seconds squared. But what's more interesting from this plot is on the x-axis here, this is the magnitude of the density gradient averaged over different scales. And again, we can make these very fine scale measurements now because these observations come from that sail buoy in this case. And what you find is that those salinity gradients get stirred up to really, really small scales. And it's only when you get down to essentially order kilometer or even smaller that you see those very, very strong fronts. And so there's this very efficient stirring out to very, very small scales. So you have strong lateral density gradients, but your mixed layer is pretty shallow. So I'm showing here time series of salinity, conservative temperature, and buoyancy that comes from the glider data now. And you can see, especially if you look at the buoyancy, that the mixed layer is essentially capped by this fresh water. And there's very little evidence of this exchange that you saw from the osmosis area. So there's, if I was to plot PV here, I've not shown this plot, you wouldn't see those low PV values indicative of the surface being carried into the interior. And you can see that here, that you don't see the salinity or the temperature anomalies getting into the interior. And so again, this is the idea that although you have very strong horizontal density gradients because you have lots of mesoscale stirring, the effectiveness in this area of that generating submesoscales that can ventilate the interior is very, very weak, again, because of this salinity capping. Now, the other thing that might be important is this idea that if you do have a field of very strong submesoscale buoyancy gradients at the surface, is there the potential here for them to interact with the surface winds and generate this, what we call an Ekman buoyancy flux, which is that schematic picture I showed you before, that with an Ekman transport, you can advect dense water over the light water and potentially have small regions of convection happening. And so it's a little bit hard with the platforms we had in the water to see that that process actually happening in real time. But there was something else that came out of these interactions with the winds that was a little bit surprising. And again, here, what was nice is because we had the meteorological sensor on the sail buoy, we had very high frequency winds. And so we were able to actually quantify the strength of individual wind gusts. And that's sort of on the left-hand side here, showing essentially a histogram of the strength of the wind stress as a function of the different surface buoyancy gradients. But what's more important are the plots on the right-hand side here, that if you look at the strength of the horizontal density gradients, given here as a function of depth, so most of them happen in the upper 40 meters, which is the depth of the mixed layer, that during periods when the winds were weak, you can see either through the blue there, which is that sort of distribution or histogram of the horizontal density gradient, or the mean value in red, that you had stronger horizontal density gradients than you had during the periods when you have the stronger winds. So that's the greater than 75% quartile. It's on the right-hand side. And so there's this picture here that actually when the strong winds come in this region, what happens is that it destroys those small submesoscale fronts in the surface ocean. And we're still thinking a little bit about why that is. We think it's because you generate quite strong shear in the mixed layer, and that's effective at destroying those submesoscale fronts. I mean, in some ways, the dynamics here are very similar to, there's been a lot of work on submesoscales in the Bay of Bengal. I mean, it's been involved in some of that work. The Mesobob study, that you see this when you have that strong freshwater flux, in that case coming in from the river's input and precipitation. Here you get the strong capping, and that the strong winds, rather than giving you these Ekman buoyancy fluxes, are actually destroying the submesoscale fronts. And then over time, the mesoscale stirring acts to regenerate those submesoscales. And so that was something that was a little bit surprising to us there. Okay, so just in the last sort of 10, 15 minutes, I want to turn my attention away from the marginal ice zone and back towards the core of the ACC. So let me maybe just pause for a few seconds here to see if there are any questions on this part of the talk before I kind of get into the last third.
Are there any influences of the surface waves, the Langmuir forcing, because that might coordinate with the wind strength that might go together with the wind strength as well?
Yeah, that's a really great suggestion. We don't know. As far as I know, there was nothing on the sail buoy to measure the wave intensity. But if there was, that was Seb's platform. He was not looked at it yet, or at least I've not been involved in that work.
Thanks.
Yeah.
Andy, this is Tom. The picture that you're describing here, it makes me wonder whether we could not use the oleander because it's crossing the north wall of the Gulf Stream, twice a week, and we don't measure winds very carefully on the ship, but it's something that could easily be added, and we do have at least in principle, the thermocylindrograph and the ADCPs. This is a combination that we might be able to use to disentangle this kind of a picture for a Gulf Stream type of front.
Mhm.
That would be really interesting because, of course, the stratification near the surface is going to look very different from this region, and to understand whether this destruction of the mesoscales is because everything is just capped at such a shallow depth, and whether that would whether the same sort of features would show up in the Oleander data set would be really interesting to look at.
Oh, yep, thank you.
Yeah, this is Kathy Donahue. So so what's noticeable about this is that the difference in the panels on the right is much more profound, sort of deeper than like 5 meters or so. Like, so the very surface doesn't really show a strong decrease. Is that because of Langmuir circulation?
It would be due to Langmuir circulation. My first guess would have been that I would still expect to see here diurnal cycles, for instance. So if there's a positive surface heat flux, that you could get these little fresh, warm surface layers that the stratification in the upper, really just a few meters, might be very different. Whereas if you're in the middle of the mixed layer, so let's say 40 meter mixed layer depth at 20 meters, that's probably a better measure of what's really submesoscale density gradients than what you see right at the surface. But Langmuir circulation, other wind wave interactions may also be quite important right near the surface. Yeah, that's a good question.
Andy, this is Peter Kernillan. Hi.
Okay.
Can you hear me?
I can. Yeah, go ahead.
So I think I've shown you that plot that's the log of the gradients that sort of looks like worms all over the place. What I think you're suggesting here is that under high wind events, they should all disappear, all my little squiggly things. Do I have it right?
I think that's the suggestion in terms of a horizontal density gradient. What this might look like in a tracer, right? And in particular, in this region, temperature is a tracer, right? Is a more or less passive tracer because salinity is governing density. I don't know exactly what happens if you were to look at the tracer spectra, for instance.
Because it's certainly something we could do. We could look at the worminess of pictures as a function of SST fields as a function of the wind speed.
Yeah, that would be interesting to look at, because it's not. Yeah, that's right. It's not immediately clear to me, sort of sitting here giving this talk, what the tracer spectra would look like and how that would evolve under these strong events. But it'd be interesting to look at.
Okay, thank you.
You're welcome. Okay, so let's kind of move on to the last part, and I'll go back to the chin strap study for motivation, but I'm going to talk a little bit more about a study we did sort of again south of Africa. The other thing we really learned from chin strap was, this was actually a separate deployment from the Drake when we went across the polar front in Drake Passage, was that as we know in the Southern Ocean, you could see in that movie I showed right at the beginning, is that topography plays a very important role in localizing where you have strong and weak eddy kinetic energy. So here's just an example in the southern part of Drake Passage in terms of the bathymetry there. It's dominated by this strong bathymetric feature, which is the Shackleton fracture zone. It is a ridge that the sill depth is probably only about about 2,000 meters instead of 4,000 meter depth. And it really separates a region of weak eddy kinetic energy upstream and strong eddy kinetic energy downstream. And you can kind of see that in the Aviso data. You start to get to latitudes where the Aviso data doesn't always have coverage, but you can also see it in high resolution numerical models. So on the right-hand side here, you see much higher eddy kinetic energy downstream of the Shackleton fracture zone than you do upstream. And so in one of these deployments, we had gliders both upstream and downstream of the Shackleton fracture zone. And you can already see some differences in just our ability to do nice hydrographic sections. So upstream, you have these more or less straight sections that are perpendicular to the continental slope. And downstream, you have this total mess because it's a much more energetic region, and you struggle to kind of keep the gliders moving across there. I'm not going to talk about this in too much detail, so I'm just going to show one figure, and I apologize that I'm not showing the, where all of this is coming from. But what I'm showing here are a time series on the x-axis, and on the y-axis here is a heat flux. In gray is just the surface heat flux, which is short wave, long wave, sensible, and latent. But the orange and green curves are essentially parameterizations of the submesoscale contribution to the heat flux in the upper ocean from a mixed layer baroclinic instability in orange, and then the second buoyancy flux in green. And the only thing I want to point out is that the magnitudes are much larger I think I've mislabeled these. They're much larger in the downstream region. So it should be the bottom one is east of the Shackleton fracture zone, where you have much stronger kinetic energy. So even though these regions are very close to each other, they essentially feel the same surface forcing in terms of the wind stress and the buoyancy flux. You see very, very different submesoscale characteristics. So if I focus in on where you might go to look for submesoscales in the Southern Ocean, we know in the Southern Ocean that the distribution of eddy kinetic energy, and in particular mesoscale strain, is very patchy. So this is a paper that was published over a decade ago by Darren Waugh and colleague, looking at these values from altimetry in the Southern Ocean. And you can see that these regions that light up are what we call these standing meanders of the Antarctic Circumpolar Current. So they're places where the ACC is interacting strongly with bathymetry and giving region to these elevated regions of eddy kinetic energy and strain downstream of that feature. And to finish up in this talk, I just want to show a few results from a deployment we did in one of these standing meanders. So this is at 30 degrees east, so it's just to the east of the southern tip of Africa. And it corresponds to...
East,
is that, I'll keep going unless there's a question there. No, I'll keep going. So this region corresponds to a gap in the southwest Indian Ridge. So on the left here is the bathymetry. I have the climatological positions of the different ACC fronts, just the polar front there is labeled. And that gap in the southwest Indian Ridge essentially ties the position of the polar front to that latitude at about 51 degrees south. And then downstream of this, you have a strong region of a standing meander and then large eddy kinetic energy. So one of the things to sort of point out here is that there's sort of call it a cascade, but there's sort of a connection between the different scales of variability in the ACC, where the flow interaction with bathymetry sets up these large standing meanders. These standing meanders, potentially because you have these strong deviations from zonal flow, give rise to enhanced eddy kinetic energy, and these are very effective at stirring tracers. So there's this beautiful picture. Unfortunately, that picture of chlorophyll does not come from when we had instruments in the water, because it's always cloudy in the Southern Ocean, and you get a picture like that once a year, once every other year, something like that. But just a beautiful picture right where we had the gliders at a later time, where you can see, that this front separates, has a big signature in surface temperature, but also is very effective at stirring out tracers like surface chlorophyll. And then, of course, the other reason this area is really interesting is because you're sitting right at the polar front, you're at the location where you switch between what we call an alpha ocean and a beta ocean. So north of the polar front, you're temperature stratified. South of the polar front, you're salinity stratified. And so you can sustain, for instance, very strong temperature gradients on these isopiconals in this region. It's also true of salinity and other properties as well. And you can see here, so this is the hydrographic section that's collected along I-6 South when we deployed the gliders. Again, we put in right around 51 degrees south. And this is also an interesting place because north of the polar front, you can see that those density classes that are the black curves here are isopiconals. Those density classes are ventilated right at the surface. And south at the polar front, again, you have this strong stratification at the base of the mixed layer. Okay, so what did we do? So here's another map. So latitude on the x-axis, latitude on the y-axis, longitude on the x-axis. You can see that standing meander there. So these are contours of sea surface height, these thin black curves. The color here is eddy kinetic energy, so it's quite strong. And what we were trying to do with this study was actually track one of the SOCOM projects. So hopefully most of you are familiar with SOCOM. It's a concerted effort to populate the Southern Ocean with bioargo floats to sort of look at the distribution of biogeochemical properties in the Southern Ocean that we've never had before. But these floats only sample once every 10 days. And so the goal was to actually track the float with a couple of our gliders to look at the sort of high frequency variability in these properties and provide some context to what the floats see when they only profile once every 10 days. So in this map here, you can see some black points, some blue points, which are the gliders, and then some green dots with dotted lines, which was the position of the float. We were in a very energetic region, so our ability to keep the gliders near the float was not always perfect. So you can see they get separated sort of around like 32 east. Although when you look at their position in sea surface height space, which is a proxy for the streamlines, actually they actually still remain pretty close. So the idea was that they're sampling more or less the same water properties. And so this is kind of a busy plot. I won't spend a lot of time on this, but just kind of an appreciation for the scales of variability that you see. Both of these are time series. So time is on the x-axis, and these are both showing something like 3 weeks worth of data from the gliders. As you go from the top, there's a measure of sea surface height variability, temperature, salinity. This is, sorry, I apologize, your faces are covering the axes here. This is oxygen, I think, or AOU. And then there's vertical stratification and then optical backscatter at the bottom. And so if you look on the left, this is the period when the gliders were in that standing meander region where you had high eddy kinetic energy. And so you can see just lots of variability almost throughout the water column, or at least down to about 1,000 meters. Very small scale variability, this signature of the mesoscale stirring and generating fine scale structure in both the temperature and the salinity. And as we moved further downstream, because we were vected to the east over the course of the field program, you get into a region of much weaker eddy kinetic energy, and you can see that those scales of variability become weaker. And there's a lot to take away here, but maybe I'll try to summarize by just showing this. One can look at anomalies of what we think are more or less passive tracers. So on the left here is anomalies of spice. So spice are variations in temperature and salinity on a given density surface. So that behaves more or less like a passive tracer. On the right are anomalies of AOU, apparent oxygen utilization. And again, in green and purple here, you see those anomalies in the high eddy kinetic energy region in green and the low eddy kinetic energy region in purple. And what you see is that the variability or the anomalies are much larger in the high eddy kinetic energy region. And what's interesting is that they're really enhanced not just in the surface layer, but also at depth. Okay, so these are on density surfaces, and then we're mapping them back to their mean depth. That's why you have depth on the y-axis here. So that suggests two things, right? One is that actually there are anomalies coming in from the surface and penetrating to depth, or again, recalling that you have tracer gradients on these density surfaces, that they're effectively getting stirred up in the interior. And the other thing that could be happening is that you're bringing these tracer anomalies up towards the base of the mixed layer, so that if you do have some mesoscale motions, they can move more efficiently ventilated across the base of the mixed layer. Now, you know, these maps look pretty because you're in a region of strong flow. The gliders are getting moved around quite a bit, and so it's hard to be. A lot of the analyses that we have done with the gliders, the mid-latitudes, we were more cautious about in the Southern Ocean because of what you're aliasing in terms of space and time. So to get away from that, we did a lot of our analysis in temperature and salinity space, because then it's a lot clearer where you are sort of in terms of the fronts and what are the properties that are happening. And I just want to show sort of one plot from that. So this is temperature on the y-axis, salinity on the x-axis. There are density and lines of constant spice on here as well. But I'm plotting here the temperature salinity distribution colored with the strength of the optical backscatter. And so you see at warmer waters, which is north of the polar front, you have higher backscatter. Colder waters, which are indicative of being south of the polar front, have much lower values. And you can see right in the middle here, which is sort of right where you're in the core of the polar front, you can see that these backscatter values move further to higher salinities, which is indicative of being at deeper depths in the water column, moving to higher density classes. And so there's this picture here that there's a real preference for subduction of, in this case, backscatter, which is likely particulate matter, that's happening right in the core of the front because you have this strong gradient in backscatter across the polar front here. And so to dig into this a little bit more about what's going on, I'm going to show maybe we've got two slides left here, one somewhat more technical and then one kind of a bigger picture one. So stay with me a little bit. The way we tried to break this up was to look at characteristics of both the horizontal density gradient, which again is a characteristic of the submesoscales, but also the strength of the vertical stratification at the base of the mixed layer. So on the left-hand side here, you have on the x-axis the maximum value of n squared, which is sort of always associated with the base of the mixed layer. And there are sort of two sets of contours. This red distribution would be in the high eddy kinetic energy region, and the black contours would be in the low eddy kinetic energy region. And if you just integrated over that, you get the curves at the top. And so what you see is that actually the stratification is actually stronger in the high EKE region. And that surprised us a little bit, but what we think is happening there is actually the submesoscales are pretty effective at re-stratifying the mixed layer in this region. Because if you look on the right panel now, I've replaced n squared with the horizontal density gradient in the mixed layer. And you do indeed see that in the high eddy kinetic energy region that you have stronger horizontal buoyancy gradients. Now, what you see on the y-axis in these plots is a vertical gradient of spice. So this is essentially a passive tracer measured at the depth of what we sort of assume is the base of the mixed layer, so where n squared is strongest. And if I integrate now over in the horizontal direction, you get these curves on the right, which is essentially just a PDF or a histogram of the strength of that lateral gradient in spice. And what you see is in the high eddy kinetic energy region, you have this much, much weaker vertical gradient in spice across the base of the mixed layer, which we think is a signature here of a much more effective ventilation of the surface waters in this standing meander region. And if I show that, I think in a somewhat slightly simpler way, here's the same thing. It's a histogram of the average AOU, or difference, I should say, the difference in AOU between the maximum n squared value, so at the base of the mixed layer, and 200 meters below it. And what you see is when you look specifically in the standing meander region as opposed to the downstream low EKE region, there's this, what we think is enhanced exchange between the surface mixed layer and the interior. And so I think the picture you have here is that in the standing meander, you have enhanced mesoscale stirring, generating stronger submesoscales, also bringing tracer anomalies from the interior up towards the surface, and a more effective ventilation of the surface in these regions. And so it sort of points to this idea that standing meanders could be these ventilation hotspots for the Southern Ocean. And this is I think some of the first work that's tried to get at this observationally. What we're finding is very consistent with what people have found in high resolution numerical models. So some of the first work on this goes back to Isa Rosso's work as a PhD student, where they ran very high resolution numerical simulations just downstream of Kerguelen, which is another big standing meander region, showed that there are these abrupt transitions in submesoscale velocities and enhanced ventilation. And there's a recent study that's currently in review also arguing that these standing meanders could be also very important in air-sea exchange of CO2. Again, that bringing that old carbon up to the surface in the Southern Ocean. Okay, so that's about all I wanted to talk about. I'll have one slide here of where we're going from here. I started kind of with a numerical model. I want to maybe come back to it. One of the things we're really excited about is, again, in collaboration with our colleagues at JPL, I showed you that very high resolution global ocean model. they are currently working on a very high resolution coupled ocean atmosphere model. So what you're looking at here is a snapshot of wind stress curl in a 1/16th of a degree atmosphere, coupled to, on the right, the surface ocean vorticity in a 1/24th of a degree, so roughly 4-kilometer resolution ocean. And we're very interested in what happens in these standing meanders, high EK regions in terms of ocean atmosphere coupling. And one question that I'm interested in is when we look at variations in air-sea exchange, that may be in terms of CO2, could be in terms of oxygen, to what extent are they governed by sort of large-scale changes in atmospheric circulation patterns? Or is there a role here for variability that happens in these ventilation hotspots, in these high EKE regions, to have an imprint on the larger scale budgets of tracers and air-sea exchange? Okay, so I'm right up at 8:30 here. Thank you for the questions during the talk, but I'm happy to take a few more if there's time, and I'll just leave my conclusions up.
Thank you, Andy. And I think we can start our question part. So is there any question for students first? If you have questions, just go ahead.
One I had is, I might have missed, but how the eddy kinetic energy is influenced by the topography, or was that one of the things you were discussing?
Yeah, no, thanks, Laura. That's a good question. I did gloss over that a little bit. There are a few thoughts about why this happens, but I think a pretty good way to think about this is what happens. So over most of the Southern Ocean, the ACC fronts are more or less zonal, right? So they're flowing east-west. And what happens when you hit strong bathymetry is that there's a constraint on the potential vorticity. So if we just think about sort of the barotropic vorticity, you need to conserve F on H. So you're coming along and all of a sudden H goes like this, right? And so in order to get up and over that bathymetry, typically what happens is the flow will move to the north to lower values of the Coriolis frequency. And so there is a deflection of the jets. And this actually does two things. So the first thing is that it takes that zonal jet, which started to be zonal, and twists it so it now has a meridional or north-south orientation. And if you just look at classic linear baroclinic instability, flows that are north-south have a much stronger instability and lead to more energetic eddies. But the other thing that happens when you deflect the fronts is the density gradient associated with that jet tends to contract. So you've got some density surface like this. As they tilt, they come closer together. And so you just have stronger density gradients in that region as well that can be extracted via baroclinic instability. And maybe one other thing to say is because that jet contracts, you also get stronger shear, horizontal shear on the flanks of the jet. And people have argued that you can also get just barotropic instability, like shear instabilities that happen in these regions.
Thank you.
Yeah.
Any more questions from students? I think we can open the question to everyone. So if you have questions, just go ahead.
This is Peter Cornellan. This is probably way off target, but what happens when you have very strong diurnal warming? How does that affect you have a very, very stratified layer that's 1 meter deep or 2 meters deep, but at the surface.
Yeah, I mean, in general, I don't think, so, in the Southern Ocean, it's rare that you have mixed layer depths that are maybe any shallower than about 40 meters. And so in terms of the types of motions that I'm thinking about that are going to generate your strong vertical velocities, I can't imagine that a shallow couple meter thick diurnal layer has a big impact on that. So even if you have 40 meter mixed layer depths, the time scale over which a submesoscale mixed layer baroclinic instability would act would still be on the order of a couple days.
Right.
And so I don't think this necessarily has a huge role on that.
I think, Peter, what you're thinking of is very much important as you get towards the tropics. And the tropical oceans are even, up to like 20 north. In the Bay of Bengal, we see lots of these diurnal warm layers that you're talking about. And with the student, we are just beginning to make some toy models to think about how they might interact with the submesoscales. But I don't have very much more to add at this point.
Right. Thanks to both of you.
Sure. I mean, I think
very, very nice talk, Andy. I have a question.
Go ahead.
So in one of your snapshots, this was, I forget how many slides ago, we saw a lot more variability with the gliders, where you showed us about, a few panels on the left and right.
Yes.
There's some very interesting subsurface warm signatures I see in panel B, roughly about 200 meters depth or so.
Yes.
What's going on there?
So I'm not sure that you can't see my mouse, right?
No.
Okay, so that's a little bit of a shame, but no. So this is really interesting. I mean, well, as you know well, right, that these are clearly very important. There's three-dimensional motions that are going on, right? So one thing to look at here is, so if you look at day, say 135, right, you have those very cold temperatures. That's indicative of winter water south of the polar front.
Yes.
I think what's a more interesting feature here is if you now go to like day 127 to 128, you see that winter water, but you see this like very thin layering happening, right? Yeah. And I think what you're seeing here is that what's really interesting is that there is that warmer water that's sort of getting below the mixed layer, but once you get below the mixed layer, it's almost like the submesoscales have done their job.
Yes.
Right? And at that point, the mesoscales take over. And partially what gives rise to this layering is that you do have this very vigorous lateral stirring, but there is some vertical shear as well.
Yes.
So as you move downstream, right, all this horizontal stirring is not vertically uniform. It's not coupled. And so very quickly you get decoupled and you get this cold layer, warm layer, cold layer, warm layer. And you can see that very nicely in the temperature because it is the passive tracer. It's not the stratifying component.
Yes.
And so, I don't know if I summarized this really well, but I think what's important in the standing meanders is that the submesoscales may only have to do the job of getting tracer, or if it's particulate matter that you care about, across the base of the mixed layer. And as long as that's effective, and it will be effective in these places where you have strong mesoscale strain, it can hand off the job of doing the stirring and the ventilation in the deeper ocean by this along isopycnal mesoscale stirring.
Yes.
And so it's, the mesoscales giving rise to the frontogenesis of mesoscales, giving you strong vertical velocities, and then the mesoscale take over as well and do the ventilation. It's a putting all those pieces together is a really fun problem. And to see it coupled to the standing meander, right? The reason why the mesoscale is there is because of the much larger flow and that they're all very strongly coupled. It's really neat. And just to finish, I think what we don't understand is what sets the variability of those sort of structures, right? So how does the standing meander respond to changes in the wind stress, both on long time scales and short time scales?
Fascinating. This is very, very interesting. I think that I was just scaling in my mind the height you have here with the Bay of Bengal, because we see the description you gave, we could have just changed the names and depth scales and some of the stratification scales.
Yeah, no, I've been reading those papers.
The physics would be very similar.
Yeah, exactly, for sure.
Thank you. Very nice talk.
Yeah, we've got to, one thing to do is actually some of the nice work that you've been involved in comparing like the spectral estimates and the slopes of Spice, for instance, would be nice to do here in the southern.
Yeah.
So Andy, this is Randy Watts. This is probably a bit off the wall, but how does this shed light, perhaps, on the carbon uptake from the atmosphere down into the ocean, whether there's a tendency to sequester it into the intermediate waters, or this winter water and drawn further to the north, or is it being released from the deep waters upwelling there? There's this controversy, but it was, I think, still in the Southern Ocean.
Yeah. Well, okay. So right at the beginning, I mentioned that the work we did on this Standing Meander project, which has the acronym SOGOS, is in collaboration with Allison Gray at the University of Washington and Drew Balwada. So Allison's 2018 paper, which was like really the first cut at looking at the fluxes from the SOCOM floats, was really interesting, right? Because south of the polar front, there was much less outgassing of CO2 than previous estimates had suggested. I'm sorry, no, sorry, there was much, let me get this right.
Much more ingassing.
There was much more, that's right. There was much more outgassing, right?
Yes, yeah, that's right.
Yes, okay. And so, and that was really, and by a lot, right? And so one of the things, I mean, this is my sort of wild idea of why that is, all the estimates in the past, especially in the winter, all of them came from Drake Passage, right? And in Drake Passage is exactly where I showed you before, that you have all of this sea ice melt from all of West Antarctica being filtered into this very narrow region in Drake Passage. And so I think ventilation in Southern Drake Passage, even in the winter, is very weak because you're capped by this very, very strong stratification. And now, once the floats sampled a much more diverse series of regimes in the Southern Ocean, and maybe got into some of these standing meanders, they got into places that were much more efficiently ventilated than what you just had from the underway data from the Gould all those years, right? That's one suggestion. To answer your question, Randy, I don't think we know. And you know, Allison's first cut was like, let's globally look at the CO2 fluxes and separate them out by frontal zones, which is the first thing you would do, like north of the polar front, south of the polar front, marginal ice zone. And now Channing Pren, for instance, who's a grad student at Scripps, is starting to look at the basin by basin breakdown. And I'm very interested to start doing, and we've got a student starting to work on this, using more dynamical ways of binning the data. So if you just take those floats, which are in high EKE, high strain regions, what do you see as opposed to regions where the ACC fronts are more zonal? It's a little unclear yet whether we have enough float data to statistically do that sort of a breakdown, especially because the floats get evected out of these high EK regions relatively quickly. But that's one reason one direction I would like to go to address that question, Randy.
Very good, thank you. Yeah, right.
Hey, Andy.
Hey, Jamie.
That is such a great talk and so ambitious to show us all these different places that you've been. I have a kind of practical question, which is when you have the sail buoy and the gliders going together, I think in the end, so I'm trying to wrap my head around which figures came from sail buoy and which figures came from the glider, and how you make those work together, because the sampling schemes are so different, right? One's doing these longish transects.
Yeah, sorry, I should have been more careful about that. So most of the data actually came from the sail buoy. So the only, as you know, the gliders, we typically, when we're in the Southern Ocean, we are prioritizing duration. So leaving them out there for as long as possible, as opposed to necessarily resolution. So the gliders are going down to 1,000 meters, which means the horizontal resolution is order 3 to 5 kilometers. Right, the sail buoy being a surface platform is really measuring just at the surface at much higher resolution. So this particular plot, for instance, is from the sail buoy. These plots where you're starting to see actual vertical structure, that comes from the glider.
Okay, I see. So you use the sail buoy to get at these like M squared, the lateral density gradients, kind of thing, and then and the winds.
That's right.
Then the gliders tell you about the mixed layer depth, the penetration of the anomalies to depth, and that kind of thing. And do you care about how close they are? Or you do your kind of butterfly and your transect and just hang them together in that sense?
Well, yeah, so you have to be, if I go to that last slide from that section of the talk, the surface density gradient, you would want that to be coupled with the winds, right? Because even at the scales of which you're doing that butterfly, it is possible to see very different submesoscale structure wherever the glider is compared to the sail buoy. So I think the point I guess was trying to make here is that we have done things like, okay, let's take the characterization of the surface density gradient from the glider and just use reanalysis data and estimate things like the Ekman buoyancy flux, because you know something about the strength of the winds and their orientation. But the reanalysis data is, you know, averaged over, depends on the product you use, right? But a couple hours. And what we're actually starting to see from the couple model is just the intermittency that you get from having a fully resolved atmosphere acting over a variable surface ocean gives you very, very different results from what you get if you just make inferences from reanalysis.
Oh, wow, that's cool too.
And so in this case with the sail buoy, you get these, you know, a typical wind stress for the Southern Ocean on average is like 0.1 or 0.2 newtons per meter squared, but you can kind of intermittently just get this very strong wind gust. And so it's starting to think about how those very strong but brief in duration winds might impact the surface ocean.
Okay. Great. Thank you so much.
Yep.
Max,
yeah.
wrapping up.
You can just go ahead.
Okay.
Go ahead, Melissa.
So you mentioned that the mesoscale stirring is kind of taking over once some of these anomalies you know, enter into the main picnic line. And I'm wondering if you ever see circumstances at depth below the mixed layer where you have criteria that could indicate that submesoscale processes may still be acting and important. And obviously then it's isolated from things like air sea flux, wind, but may still have something like frontogenesis or something else that could be happening at depth that could modify some of the properties there.
Yeah, so I already showed way too much material. And the topic that missed the cut at the end was exactly that issue. So I appreciate it's getting late, so I'll do this very quickly. But some of the work that Leah Siegelman led when she was at Caltech was this idea of looking at the importance of frontogenesis at depth in the Southern Ocean and whether you get submesoscale. So rather than using a glider, she used data from an instrumented seal. So she had this amazing data set. So the seals are cool because they're even higher resolution than the gliders. They move faster than the gliders, so they go like right through these coherent eddies. And you get these beautiful time depth series here where you can see very clearly those mesoscale eddies it's cutting through. You have these very sharp horizontal buoyancy gradients on the edge of the eddies. And I'm going to go through this at breakneck speed, right? But the thing that she found that was really amazing is you could take, so for people who've looked at this before, you can do things like estimate finite size Lyapunov exponents, which are going to highlight these straining regions. And if you match up where the lateral density gradients are in the interior now, not just at the surface, with these straining regions, they line up almost exactly. So on the left here, where you see this yellow, is sort of exactly in those strong straining regions. And so you are getting this frontogenesis at depth. And then I didn't end up showing these slides because it gets into a little bit of detail of how you try to then take that information and link it to a vertical velocity. And of course, if you're interested in that, I can forward on the work that Leah has led over a couple papers now. But she finds evidence that you will get these order many tens of meters per day vertical velocities in the interior that could have very strong heat fluxes associated with them. It's really neat. And so when we were writing this, I was really nervous. I was like, I don't know. I mean, those are big velocities in the interior to have. And subsequently, I mentioned that paper by Xiaolong Yu, who did a similar analysis for the osmosis data, and he finds very similar things even in the Northeast Atlantic. So there are at least a couple of papers out there now that suggest that that these submesoscales are not only near the surface.
I think this is very important because, you know, it's not just focusing on export from the mixed layer into the pycnocline. If you're really going to look at longer term sequestration, you need to be able to move. If it's carbon export that you're looking at, you need to have that move below, you know, sort of the deep winter mixed layer threshold. So it requires some other processes that are happening in the pycnocline to continue to move that carbon downwards. And
yeah,
this can be one of them, right?
Mm-hmm. And that is incredibly interesting. And the other thing that's really cool in the Southern Ocean is that penetration depth also influences whether you end up on the upwelling or the downwelling limb of the overturning too. Like, are you in intermediate water that's going back down or deep water that's coming back up? And so I think yeah, how the submesoscales couple to exactly which density surfaces you imprint those anomalies on is really neat.
Yeah, because then that plays into the larger scale circulation, which then can also act to have this longer term sequestration effect.
Absolutely. Yeah, no, that's really neat.
So Andy, this is Amit again. I have just one last question. So the time scales that you're thinking of associated with these submesoscale motions, even when you have these gradients deeper in the interior, is what?
Oh, you're asking like, is this the same thing as a mixed layer baroclinic instability?
I mean, yeah, so what time scale would you associate with that? Is that more like a, fraction of an inertial period, or are you thinking, or is it longer? Because
no, I think it's longer than that. I don't have a good answer, so I'd be reluctant to put a real number on that. But no, I mean, these straining regions are persistent for long periods of time. So
right.
I think, it would take you, or at least many days, right, for that front to really, really get sharp in the interior.
Right.
I guess I don't have a good sense for,
because these
process of the frontalysis, right? How that's
right.
actually destroyed.
Right. I mean, the frontogenesis arguments we make, generally have been applied to these QG omega kind of with numbers and that kind of theory, and people have tried to make all kinds of modifications to them, maybe by either including more nonlinearity or other kinds of effects which are generally discarded at QG. But I wondered, and those typically do give you the asymmetry in the vertical velocities. They do give you bigger numbers than one would get from QG omega.
Yeah.
But I wondered how much of that is sort of resolution dependent and time dependent. But you're right. If there are persistent effects in the if there's a persistent strain, then that would certainly lead to persistent vertical velocities.
Yeah, that's right. I mean, one of the creative things that Leah did with this study, right, was to say, I have empirical evidence that I can link the lateral density gradient seen in the seal data to the FSLEs, right? And so now I can take the FSLEs actually as a proxy, and there's an empirical relationship between the two to actually get that very small lateral density gradient. In particular, get the orientation of it right, because if the seals are not exactly perpendicular to the fronts. And I think, I mean, she's now moved on to a postdoc at Scripps, but I think one of the things she was thinking about is to what extent can you start using the FSLE fields globally to start understanding what is the impact of density gradients. I think there's some work to be done because she did this study in a standing meander, which is a very unique regime of the Southern Ocean. And to the extent to which those relationships hold elsewhere is something that she's still looking at.
Great. Thank you, Andy.
Yep, you're welcome.
Any more questions? Oh, I think now everyone, there's no more questions now, so we can end today's seminar. And let's thank Andy for the great talk today. And if you have more questions, maybe you guys can contact Andy directly and discuss with it. Okay. And thank you, Andy.
Thank you.
Yeah, thanks for your attention today and showing up. It was
very good. Very good. Thank you.
Thanks.
Okay, bye everyone. Have a great day. Have a nice weekend.
Bye. Thank you.